Introduction to Statics. What is statics? Well, it's the study of forces and their effects on a system in a state of rest or uniform motion. Here's an example of a system that's in a state of rest. This bridge here is static. Here's another example of a system that is at rest. This other bridge, lots of trusses that we can see. All these little things here are little pieces of trusses. If I take this car here, and if I move it at a constant speed, then it's static. It's a uniform motion. Same speed throughout. So there's 3 different examples of things that are static. There are some static principles that we want to discuss, and they are based upon Isaac Newton. Newton's first law of motion, which is known as the law of inertia. An object in a state of rest or uniform motion will continue to be so unless acted upon by an outside force. So if a chair is sitting here in this room, that chair is going to continue to sit there unless an outside force acts upon it. Like someone comes along, maybe a little bit of a jerk, and decides that they're going to kick this chair. Kick, and then the chair falls over. If you were to take a car, take this car and put it in neutral, and just push the back of it gently and let go. This car, unless acted upon by an outside force, will move forever. If you ever pushed a car and you let go, you've noticed it stops. And why does that happen? What happens because of gravity? If gravity did not exist, and if friction didn't exist, those are 2 outside forces acting upon a car when you're pushing it. Friction, with the tires hitting the ground, and gravity that's pushing down on the car. If those 2 things weren't acting upon it, if you gave this just a little tap, this car would move forever at that constant speed. Static principles. Newton's second law of motion. The acceleration of an object is proportional to the net force acting on the object. Let's first take that. Acceleration is proportional to the force. What that means is, as acceleration gets bigger, then the force also gets bigger. And the converse is true as well. If the acceleration gets smaller, the force gets smaller. Those 2 numbers, force and acceleration, move in the same direction. If one gets bigger, the other one gets bigger. If one gets smaller, the other one gets smaller. That makes sense because the more force you put on an object, the more it's going to accelerate. Put a small force on an object, it's going to accelerate just a little bit. And the second part to this, the acceleration of an object is inversely proportional to the object's mass. The acceleration is inversely proportional to the mass. If two numbers have an inverse relationship, it means as one gets bigger, the other one gets smaller. I think that makes sense. Let's say that we have this cube and its mass is 100 pounds. Let's say you have a different cube and its mass is 10 pounds. And let's say that you are pushing up against this. You have one eye, apparently. You're kind of a freak show. And in the second case, you only have one arm. Anyhow, let's say that your top speed is 5 miles per hour. Which of these scenarios, scenario 1 or 2, are you going to reach your top speed faster? We're obviously going to reach your top speed faster pushing the one that has the less weight. So here you're only pushing 10 pounds. You're going to excel quicker. Here you're pushing 100 pounds. Your acceleration is going to be slower. So once again, inversely proportional means as one number gets bigger, the other one gets smaller. As the mass gets bigger, the acceleration gets smaller. Here, as the mass gets smaller, the acceleration gets quicker. Newton's third law. It's the law of motion. Third law of motion. For every action force, there is an equal and opposite reaction force. So here's an example. Here's the ground. And here is a dude. Or perhaps it's a woman. I don't want to be sexist, so we'll make it half man, half woman. As this woman, man, woman, this thing is standing on the ground, he, she is pushing on the ground for every action force. So that's an action force. It says there's an equal and opposite reaction force. Guess what's happening as this thing is pushing down? The ground is pushing back. That's a reaction force. Now, that sounds ridiculous, but if that weren't true, when you stepped on the ground, your foot would go clear through, and you would just sink. When you go to a wall, and you push on that wall, that wall's going to push back. If it doesn't push back, you're going to go clear through the wall. That's Newton's law of motion. Right now, take your hand and push it down on your desk. Push it as hard as you can. Every pound of force that you put on the top of that desk is matching your force in the opposite direction. Otherwise, your hand would go through it. Equilibrium. Static equilibrium. A condition where there is no net external forces acting upon a particle or rigid body, and the body remains at rest or continues at a constant velocity. Here's an example. This building here is in a state of static equilibrium. If it wasn't, it would start floating up in the air, or it would sink into the water. Translational equilibrium. The state in which there is no unbalanced forces acting on a body. Notice it says there's no unbalanced forces. There could be forces. In fact, there are forces. But they're all balanced. I'll give you a couple pictures here. This bridge here is unbalanced. So to be in equilibrium, there has to be no unbalanced forces acting on the body. This has some forces that were unbalanced. This bridge here is balanced. That's why it's in that translational equilibrium. I'm going to take this opportunity to explain some math symbols here. This symbol is a Greek letter. It means sum. So for example, if I were to say sum all the x's from x equals 2 to 5, that means you take a 2 and put it in for x, add to it, putting a 3 in for x, add to it, putting a 4 in. Keep adding consecutive integers till you get to this top number, till you get to that 5. You would sum those and you'd get 5 and 5 is 10 and 4 you get 14. That's an important symbol that we're going to be using here with statics and equilibrium. So specifically, we are going to have forces in the x direction, and we're going to also have forces in the y direction. Since it says up here that the translational equilibrium is a state in which there is no unbalanced forces acting on a body. So if you take all your x forces and you sum them, it should always equal 0. Likewise, if you sum all of your y forces, it should equal 0. If those two things don't sum to 0, then you get this, a bridge that collapses, an unbalanced system. If it's not static, meaning it's balanced, you're going to have major problems. Lots of money, possibly loss of life. Going back here to the x and y idea, we refer to x as a horizontal motion, left and right. We refer to y as a vertical motion, up and down. X is left and right, y is up and down. Rotational equilibrium. The state in which the sum of all clockwise moments equals the sum of all counterclockwise moments about a pivotal point. Let me remind you what a moment is. A moment is the same concept as work. If you recall, work is force, pardon my F, is force times distance. And work is always measured linearly. It's always a linear motion. A moment same concept here. It's force times distance, but the force is always perpendicular to the distance. Because of that, you're going to have rotations. This is clockwise, that's the way a clock goes, or counterclockwise, the opposite way that a clock goes. Here's an example of rotational equilibrium. This teeter-totter is perfectly balanced. So it is not rotating either direction, not clockwise nor counterclockwise. We have some more static principles here. We have scalar quantities and we have vector quantities. Scalar and vector. A scalar quantity is a physical quantity. By the way, quantity means a number. A physical number that has magnitude only. The examples: mass, length, time, temperature, pressure, speed. So if I were to say I weigh 50 pounds, my magnitude is 50 pounds. If I'm 4 feet tall, my magnitude is 4 feet. 30 minutes, that's a time, that's a magnitude. Vector quantities. A physical quantity that has both magnitude and direction. So vector is the same thing that scalar is, but it includes a direction as well. So example, Jimmy is going 55 miles per hour. So far that's a scalar. But then I say north. Now it's a vector. It has a magnitude. This here's the magnitude. And it has a direction. This is my direction. We call that velocity. Most people call 55 miles per hour speed, which is true, but if I say if it's a velocity, I have to also include which direction I'm traveling. Other examples are moments, force. Those are all have are vector quantities. So what is a force? It's the pushing or pulling interaction of objects. A vector quantity, this is important, I don't know if you've seen vectors before, probably haven't. A vector quantity is defined by its known magnitude, that's a number, its direction, and point of application. Let me show you what that would look like in a coordinate plane. Here's an x-axis and here's a y-axis. Let's say that we have this vector. Let's see here. Like so. That is a vector. Magnitude. Let's say that the length of this vector is 5 feet. Direction. Let's say from the x-axis we are going counterclockwise, that's a positive angle. Let's say it's 40 degrees. More specifically, we could say 40 degrees north of east. And a point of application. Well, the point of application, I can't draw my point over there, but it's right over here. That's the point of application. So starting here at the origin, we're going to go 5 feet in the direction of 40 degrees north of east. North of east means you start in the direction of east and you go north 40 degrees, which gives us this magnitude, this vector, I should say. Force units. There's 2 different systems that are used. One is the British system, which uses pound force, which is abbreviated LBF, pound force, LB, pound, F, force. Then there's the international system of units, which uses newtons. So how are those 2 things related to each other, newtons and pound force? 1 pound force is 4.448 newtons, which means that 1 newton is equal to 0.2248 pound force. I would not memorize both of those. I would memorize one of them. I'm probably going to memorize this one right here. If you know one of these, then you can derive the other. Simple algebra. Let's say that you've chosen to memorize this one, and you want to know what 1 Newton is equal to. You would simply divide both sides by 4.448, and 1 divided by 4.448 is this number here. So, if given the choice, I always choose to memorize one thing and derive the other ones from it, because I don't have time to sit around memorizing things. Principles of static equilibrium forces. Static equilibrium force principles. Forces always occur in pairs. Pairs means in twos. Force pairs act in opposite directions and have the same magnitude. Example. Let's say that we have this vector. It's going in the direction that you can see here, and it is 5 newtons. Its pair would have to go in the opposite direction, and it would have to be the same magnitude, 5 newtons. Another example, let's say that we have this one force that is going clockwise, and it's going clockwise, that's the direction, and its magnitude, let's say, is 50 pound force. And that means there has to be in static equilibrium, there has to be another force going in the opposite direction. That would be counterclockwise. That's its direction, and its magnitude would have to be 50 pound force. And we could go on all day here. We have a vector going to the right, and it's 10 pound force, and its pair is a vector going to the left, and it's 10 pound force. Forces always occur in pairs. Forces act in opposite directions and have the same magnitude. Fact. Force components. A single force, and we're specifically probably going to be talking about vectors, can be replaced by component forces if their combination produces the same effect as the original force. Let me show you an example. Once again, let's say that we have a coordinate plane. And we have this vector hanging out. So this is point A down here. So we would call this the force at A. This is a single force right here. It's just one thing. What this is saying, that we can take that single force and we can replace it. We can replace it with component forces if their combination produces the same effect. So let me show you. I'm going to loosely translate this vector over here. I say loosely, meaning I'm going to put it dashed so you can still see the idea of what that vector would be. By the way, should note, geometrically speaking, when you have this shape right here, it's called a ray. And a ray has a starting point and it goes forever in one direction. This is not a ray. It looks identical to a ray. This is a vector. A vector does not continue to go on forever. It has a magnitude, it has a length. A ray has no length. This vector stops when it gets to here. This arrow is just showing you which direction that it's pulling, which direction it's going in. So if this whole thing were to move, the whole thing would move. It wouldn't get longer. Once again, because it has a magnitude, that's a scale. A scalar, it's a number, it's a length. So anyhow, going back to our picture here on the right, a single force, this purple one, can be replaced by component forces if their combination produces the same effect as the original force. Well, if we were to go to the right, this length, we would call this the force of A in the x direction. And if we were then to go up, which we would say the force at A in the y direction, that would get us to the same location as we would in this original picture. This is the combination that produces the same effect. As far as talking about a coordinate plane, Cartesian geometry, let's say that this force vector started at 0, 0, and it took us to the ordered pair 3, 4. So our destination was right here. In the second picture here, let's say that we went to the right 3, and then we went up 4. Takes us to that same ordered pair 3, 4. So once again, we combined a horizontal and vertical motion to get us to a point which could have gotten there to the same place just by going at a diagonal to that point. It's important that you understand that those are the same thing. Look different, different ways to get there, but the end result is the same. Resultant force. A single force that has the same effect as two or more concurrent forces. Let me give you an example. Here we have this cube. Specifically, it's a companion cube. Here we have a version of Link, and let's say that Link is pushing on this cube. So he's pushing in the x direction left, and let's say that he's pushing it with 10 pounds of force. That's a single force. It says that single force has the same effect as two or more concurrent forces. So this is the single force that you see here in this picture. We have Link pushing against this companion cube. Now let me show you what two or more concurrent forces look like. So down here we have, well, pardon me, we have two concurrent forces. We have this smaller Link here pushing on the companion cube with 5 pounds of force. And we have this other Link here pulling on the cube going in the same direction with 5 pounds of force. What the resultant force is saying is these two actions here are equal to each other. Up here at the top, we got this big Link pushing to the left with 10 pounds of force. That is equivalent to two small Links pushing and pulling, each with 5 pounds of force in the same direction. 5 plus 5 is 10, or 110 by itself, it's equal. Another example, let's say that we have this block, and we got someone on this side pushing with 15 pounds of force, and we have someone else on this other side pushing in the opposite direction with 7 pounds of force. What's the result of that? Well, the result of that is equal to 8 pounds of force going to the left. So the guy that's over here on the left side, he's not stopping the guy from on the right, he's just making it harder. So basically, you sum these concurrent forces. If they're going in opposite directions, you would denote one as a negative and one as a positive.